Hello, how's it going? Hello from Hobbs. Say hello, Hobbs. Say hi. Well, we'll get to talk more about functions today, and we'll do so with an application example of heat transfer, Newton's law of cooling. You can see there that right there, the amount of heat transferred is proportional to the area of the surface, and the difference in the temperature of the surface and the exterior. And then there's this heat transfer coefficient. So this is a key principle in heat transfer used in mechanical and chemical engineering, and something you need to understand. And we'll practice making functions to calculate the heat transfer coefficient, or not the, as well as the amount of heat transferred. So the heat transfer coefficient as well as the amount of heat transferred. First, we'll talk about properties of functions. So this is a follow-on to the previous two videos, but function values within a function are specific to that function, and you can't really reassign a global function variable to a new value. So let's just show that. Let me I'll download my IPYNB file, and I'll open it up using my Jupyter Notebook. So let me run this and show you that there's an error. So we have an error, local variable x referenced before assignment. So here we have a global. I say global because this value of x can be used anywhere in the code because it's not within a class or a function. And I'm using it here to assign a new value for my function. So I take my input to my function and add it to my global variable. And when I try to assign it here, the global variable within the function, it results in an error. And it does so because now it thinks that this x is a local value, and it doesn't like it. This local variable x referenced before assignment, it's thinking x is a local variable within the function. So in order to get this to run, I'm going to comment this out, and you can see that now my 43, input value of 43, when I call my a function and I add 5 to it, I get 48, and my global x value is still 5. So similarly, if I have another function and I have a variable within that function, I can use it within the function just fine. I can use my input and add it to my variable. However, when I try to print it outside of the function, it's going to give me an error. It says a variable is not defined. So and more simply put, let me just comment this out. Outside of the function, if I say print a variable, it says it's not defined. And you're saying, wait a minute, it's defined right here. Well, it's outside of the function, so if I print inside of the function, it will print it. Let's see, let me comment this out. Oh, I have to call the function to get it to print, right? Another function, 34. So it first prints my variable, and prints the total, or returns the total, which is 34 plus 10. So if I comment this out now, it's going to give me an error because it's not defined. So I hope that's helpful. It's called variable scope, in that variables within functions or classes are specific to that area only. So moving on, so if we have external flow across the cylinder, here's the temperature of that flow, and then we have a temperature of the surface of the cylinder. And to find the amount of heat transfer from the rod out to the surroundings, I need to calculate my heat transfer coefficient. And one way to do that is with a Nusselt number, and this is a dimensionless heat transfer coefficient where you de-dimensionalize with the diameter of the rod and the thermal conductivity of the rod. And there's relationships. So people have worked for scenarios like this to define what that Nusselt number will be depending on the flow characteristics. The Reynolds number, you'll learn about that in fluids class, and the Prandtl number in heat transfer class. But for this case, you don't need to know specifically what they mean, but here's some numbers for what C is and what N is, and we'll talk about the Reynolds number and Prandtl's number quickly. But here we're going to use an object or a class definition. So for our medium here is the air or oil or whatever it is that's flowing over the rod, and we have a thermal conductivity of the medium and the density of the medium, specific heat of the medium, and the dynamic viscosity. So these are properties of the medium. And the reason you want to use classes for this problem is it's easy to confuse the different properties of the air versus what the rod is for the different relationships that are given. So we specify here the medium, and then the Reynolds number for the medium, which is the rho density times the velocity times the characteristic length divided by the viscosity. So in this case, it's the medium's density, and then you're going to feed it a velocity and a diameter, a characteristic diameter. Here's the function for Prandtl number, and again we use self here to be able to refer to these variables for the specific object. And so self mu times self heat capacity divided by self k, this is the Prandtl number of the medium. And then here's the Nusselt number for cross flow, and we have some if statements or conditional statements to identify these scenarios here of different Reynolds numbers conditions for different C and N values, and then we're just going to return that Nusselt number. And here we set up actually create a medium, which is air. So that's our airflow, and there's not any global variables in this definition here. It's all within this class. So here's our function to determine the heat transferred. That Q will specify velocity, all of these in SI units, the diameter of our rod. It's a big rod, one meter diameter. Area of the surface I specify, and that of course depend on the length, and then the temperature of the surface and the temperature of the air surrounding it. So I first get my Nusselt cross flow from my Nusselt number from the air. From this guy, I'm just using the dot notation to call this function here for that specific object, air dot Nusselt cross flow cylinder with the specific velocity and the diameter of the rod to get my heat transfer coefficient. And then using the other values, I can determine my Q convection. Now this is of course a function of the velocity. So I'm going to just print all of that. Well, calculate it at a number of different velocities, and you can see the heat transfer as a function of velocity. You'd expect it to increase with increasing velocity, which it does. And so here's my little plot showing that. So I've got an array of different velocities. I've got here a different rod nut diameter than initially calculated here, but I'm specifying that in a rod length and then calculating the rod area. And then for each of those velocities, doing a little array, or actually a list. And so this is a for loop on the same line because it's for each in velocity. Here's my velocity arrays, and for each of those I'm sticking that velocity inside my function to determine the heat transfer coefficient, or the heat transferred. It's also the heat transfer coefficients found in there, and then plotting my two arrays. my velocity versus my heat transfer, and then labeling that. So that is one way to do it, using classes. However, you don't have to use classes. I highly recommend you do. It's very helpful to remember which property goes with which. If you don't do that, then you have to keep track of it on your own. So for instance, here, if I don't use objects, I can just define a Nusselt number that's a function of Reynolds and Prandtl numbers. Do a good job of labeling my variables what they are. Or the thermal conductivity, the density, heat transfer coefficient, and the mu values here. You don't necessarily need to understand all this for the class as far as the scientific principles, but you'll be given the equation and the symbols to use in that equation. So here I've got those things defined, and then I'm making an array of Q. I start with an empty array and then use a loop after defining my velocities, and then do the similar thing in a loop and fill up this array for Q with an append. So it's actually a list, and the list has a method called append, so we're using that dot notation. It's an object, and then I'm adding to that this right here, similar to above, and then I'm plotting it, and we get the same answer. So it can be maybe you don't want to use classes. Here it may seem more straightforward, but when things get more complex, and it's easy to get confused which K is which, where do I use it, it's very helpful to use objects. And as code lines increase, sometimes you get lost at which global variable is being used, or have you defined it differently in different places. And so that variable scope can be very helpful to use with classes. And pretty much all of the professional programs that you use program with objects. So just a good practice to get to know how to use them. God lives and loves us. Hope you have a great day.